On example 2, use the graphs of f of x and g of x and the limit laws to evaluate the following limits. Now remember, very importantly, that we can only use the limit laws under the condition that the limits actually exist. The individual little pieces of the limits exist. So when we go to evaluate that, that's the first thing that we're going to check. Okay, so we can see that from the graph we have the blue one being our f of x function, and then the green piecewise function there being our g of x function. Number 1, number the first. We have the limit as x approaches negative 2 of f of x plus 5 times g of x. So it looks as if we are using the sum law and the constant multiple law. Again, I can only use those if the individual limits, the one for f of x and g of x, exist. So I'm going to check that first. I'm going to check the limit as x approaches negative 2 of f of x separately from the limit as x approaches negative 2 for the g of x function by looking at the graph. So on my graph, at negative 2, the blue function, the f of x function, oh no, there's a little point of discontinuity. It's our googly eye that fell off of our somehow this fell up. Maybe somebody turned our project upside down. Does that affect the value of the limit here? In this case, it doesn't, because our function is still approaching the same number from either side, and that number looks like it's 1. So the value of the limit here for the f of x1 is equal to 1. Let's take a look at the g of x. So on g of x, come down here to negative 2, and we have a nice, neat linear portion. Nothing strange is happening. We're approaching the same number from the left and the right, and that number looks like it's negative 1. Okay, all of this to say that we're totally allowed to use our limit laws. So let's break it up. We have the limit as x approaches negative 2 of f of x plus 5 times the limit as x approaches negative 2 of the g of x function. So I'll go ahead and fill in my values here. I had a 1 for the f of x function plus 5 times the negative 1 for the g of x function. Do a little bit of arithmetic and get, I think, negative 4. You may have to use your calculator to confirm that, but I'm fairly confident in that number. Okay, so that's quite a lot to write down for this problem that seems very, very simple. Now, as far as this notation goes, understand that a question like this could appear on the AP Calculus exam on either the AB or the BC test, in the multiple choice section, or in the free response section. If it's multiple choice, nobody is aware of your notation at all. They don't see any of your work. They only see your answer A, B, C, or D. If it's in the free response section, however, the graders are very particular about rigorous notation. And so you risk losing some points if you don't have notation that looks sort of like this on these kind of limit problems. And it definitely comes up when we start to look at something called L'Hopital's rule. Let's look at number 2. Number 2, it looks like we have a product this time. So the limit, this one I think is going to 1 of f of x times g of x. And again, I'm tempted to just break it up as the limit as x approaches 1 of f of x times the limit for g of x. But I want to verify that each of these individual limits exist first. And for some reason, I chose the orange crayon to do this. So the limit as x approaches 1 of f of x, we'll see what that one is. And also for g of x by looking at the graph. All right, this time we're at 1, and on the f of x function, oh, this is fantastic. It's nice and continuous here, and it looks like from either side we are approaching the number 2. Okay, that one's good. All right, now let's look at the g of x function on this one. So coming straight down here, oh, bad situation. So it looks like from the left-hand side, we're approaching negative 2, and then we jump up to negative 1 on the right-hand side. So the limit here at 1 for the g of x function technically does not exist. And it does not exist because of differing left-right behavior. Okay, what that means is that we are not allowed to use the limit laws, right? So the limit laws do not apply. So what do we do then? If we can't use the limit laws, we are going to switch to one-sided limits. So we are basically going to look at what the situation looks like from the left side separately from the right side, see what happens, okay? Now, we might be tempted to think that if we are, like, we're not being very rigorous about our notation and checking to see, hey, do each of these individual ones exist, and just go 2 times does not exist, does not exist. Sometimes that might be the case, but there are other times in which it isn't the case. In particular, on the 2017 test, AB test, it was question 15. BC test, they had the same exact question. I don't remember what number it was, where they had a very similar situation, except for it subverted that expectation. You had a number times does not exist, and then after you did your one-sided limits, the actual limit did exist. We will look at that question in class. We can't look at it here because it's a secured question. All right, so I'm going to switch to some one-sided limits, and let's look at just the left side first. So left. On the left side, I've got the limit as x approaches 1 from the left of f of x separately from the g of x function. And let me try that again. Okay, so on the graph, let's look at the left side of each one of these. So on the f of x function on blue, I'm approaching 2, and on the green one for g of x, it's -2. All right, so since both of these limits exist, we are allowed to use the limit laws, right? For both sides, the limits did not exist, but on the left side, both of the limits do exist, so the limit laws do apply. So we go, this is equal to the limit as x approaches 1, f of x, times the limit as x approaches 1. Oh, this is from the left, the g of x function should be equal to 2 times -2, which is equal to -4. All right, and then let's switch colors once again. How about purple? It's going to be super colorful. On the right-hand side, the limit as x approaches 1 from the right of f of x, and do that for the g of x function too. Let's see what these are equal to. So on the right side of 1, f of x still equaling 2, but on the green function, it looks like it's approaching -1. All right, both of those limits exist, so the limit laws do apply, and we can write the limit as x approaches 1 from the right of f of x times limit as x approaches 1 from the right of g of x should be equal to 2 times -1. What does that mean? Oh, yeah, -2. That means that the limit as x approaches 1 from both sides does not exist due to differing left-right behaviors. On the left, it goes to -4, and on the right, it goes to -2. Those two numbers are not the same, therefore this limit does not exist. So that's my conclusion here. The limit as x approaches 1 from both sides of f of x times g of x does not exist due to differing left-right behavior. All right, and I think that deserves a big fat box. That was a lot of work, right? Okay, okay, so just kind of a recap on that one. we saw that the individuals did not exist, so we switched gears a little bit and applied one-sided limits. The individual one-sided limits did exist, so we were able to use the limit laws. But when we did that, we got two different numbers from the left and from the right, and therefore the limit on both sides did not exist, because of course those two things have to match up. All right.